So far, we have seen the method, that is the graphical and tabular method to calculate the allowable pressure for a cylindrical shell under external pressure. So we have seen that the procedure is like this. So in graphical method, we are supposed to calculate two ratios L by DO, DO by T. Then we are supposed to calculate factor A from figure G given in ASME section 2 part D. And then after getting the value of factor A, we will calculate the value of factor B. If that factor A falls on that respective temperature and material chart on the left hand side, then we will not get the value of factor B. And if it falls under the curve or right side the curve, then we will get the value of factor B. Based upon the value of factor B, we will calculate the allowable pressure, and that allowable pressure we will compare with the design pressure. If allowable pressure is more than design pressure, your thickness selection is correct, and we can proceed with the rest of the calculation. This concludes the design for the thickness. And if the factor A falls on the left hand side of your temperature and material curve, in that case, we will not have any value for factor B. And in that case, we will calculate allowable pressure, which is based upon the factor A and the Young's modulus of elasticity, which we have calculated from that external pressure chart only. And with the help of this, we will calculate the allowable pressure, and that allowable pressure will compare with design pressure. And if this allowable pressure is more than the design pressure, the design is true. And if it is not, then we again have to go back and we have to opt for the options available. So what are the options? There would be the three options which will be available. One option is we can increase the thickness and reperform the calculation. Another option, we can have the stiffener rings which will be employed in between that shell courses. So we can have one stiffener ring based upon how much difference is there in allowable and design pressure. And if there is a single ring, then we will split that cylinder in equal to half. Then the L will be L by 2, what was earlier. So this with the new length, we will calculate L by DO ratio again, and we'll reperform the calculation till the time we'll get the allowable pressure more than the design pressure. Or it could be a combination of both, where sometimes we would increase the thickness and also provide the stiffener to optimize the design. So let's start with one example and see what it demands for, whether it is passing in actual whatever that internal pressure thickness is there that is sufficient for this geometry or not. If not, then whether we have to employ any stiffener. If yes, then how many number of stiffeners will be required, whether it is going to pass in one stiffener, two stiffeners, four stiffeners, or it will be a combination of all these. So let's start with this example. That is cylindrical shell. The procedure is given in UG 28. So whenever we are dealing with external pressure design, we have to go to UG 28 for the cylinders. And if we are dealing with the internal pressure calculation, we have to go to UG 27. So let's have the example. Let's say this is the geometry, what we are going to analyze under the action of external pressure. So what these geometries look like? So it's having a cylinder and two dish ends. The dish ends are of 2:1 semi-ellipsoidal head, and the shell length, weld length, that is actual shell course length, is 8,000 millimeters. Then there is a 50 SF on both the sides. So we can say 50 as the SF. SF is nothing but the straight face which will be there. So 50 SF on this side, 50 SF on this side. So we can say the tangent to tangent length, this overall length would be 8100 So 8100 is our tan length. So with this geometry, with the 2:1 semi-ellipsoidal head, let's have the design data. So what it design pressure is given to be 1.25 MPa. Design internal temperature for this vessel is 150 degrees Celsius. Corrosion allowance is 1.5. Shell ID is 1000 millimeters. When we are saying this design pressure, it is a internal design pressure. What is been mentioned as 1.25. Shell ID is 1000 millimeters. Corrosion allowance, as we have discussed, 1.5. Material of construction is SA516 grade 70, the most common carbon steel grade material which will be followed in the industry. Type of joint will be type 1, radiography will be full radiography, and the design external pressure is full vacuum. When we are saying full vacuum, by the definition of SME section division 1, full vacuum means there is a 15 psi absolute pressure coming from the outside. So there is an external pressure of 15 psi that this vessel is supposed to sustain for. And then design external temperature is also mentioned as 150 degrees Celsius. So this is the same example what we have considered in internal pressure calculation. So we have already calculated the thickness for internal pressure, and we have reached to the value of the nominal thickness. The plate thickness what we are going to buy from the market is 8 millimeters. So here we can say the nominal thickness for the internal pressure is 8 millimeters. So this 8 millimeters thickness, that is what we need to analyze for the external pressure capacity. So let's start. So we are going to proceed with step by step. So step one, that is calculation of L by DO and DO by T ratios. These two ratios are very important, and these two ratios will be utilized in calculation of factor 8. So let's start with the calculation of L by DO and DO by T. Now we are having the shell ID as 1000 millimeters, and then shell OD will be this shell ID plus 2 times of nominal thickness. So ID is 1000 plus 2 into 8 will give us 1016 mm as our shell OD. Then corroded ID is ID plus 2 times corrosion allowance 1003. This anyway in this example will not going to use value, but let us say this we have calculated. H is the inside corroded depth of the head. H is inside corroded depth of the head. When we are saying inside corroded depth, means what? From the tan line to the inner face, or we can say the ID or the inner surface of the distance, whatever that height is there, that height is nothing but the depth of that head. When we are dealing with 2:1 semi-ellipsoidal head, we know that it is 2:1. So its minor axis is half to that of the major axis, and the half of the minor axis is nothing but the inside depth. So we can say the 1/4 of the inside diameter is nothing but our inside depth. So inside depth for this distance will be ID divided by 4. So our ID is 1000 millimeters. ID by 4, that is 250, will be the inside depth in uncorroded condition. In the finished condition, whenever I will be having a plate of 8 mm, I am going to form it, and when the ID is 1000 mm, I will get the inside depth of 250 millimeters when I am going to check with the measuring tape. So that 250 mm is not the one we are looking for. We are looking for the inside corroded depth. From this 250 mm, there will be a corrosion that going to happen. So this 250 mm, that is from this place to this place, and there will be a corrosion happens in the upper side. What we can say, this 250 mm plus 1 times corrosion allowance. Remember, this is the distance and this is the radial dimension what we are talking about. So there is no addition of 2 times. There is only addition of 1 time of corrosion allowance, because this is going to happen in only one direction. Correct. So there is, if it would have been a complete ellipse, then we might have considered it twice. But here it is not a complete ellipse; it is semi-ellipse. So the corrosion will happen in only this direction. So because of this, the corroded inside depth will be is equal to ID by 4. That ID will be the finished ID plus 1 corrosion allowance. This is what we need to consider. Remember, as per UG 16, all dimension must be in corroded condition. So let's calculate this, which will be ID by 4 plus corrosion allowance. So it will be ID is 1000 divided by 4, it becomes 250 plus 1.5, it becomes 251.5 millimeter. You don't have to calculate the corroded diameter and divide it by the 4. It will give you the wrong answer, because in that case we are considering 2 times the corrosion allowance, which is not the case. The corrosion needs to be considered only in one direction. So our value is 251.5. So this value of H we need to consider. This tan to tan length has been given to us as 8100 mm. SF is been given to us as this. The line of support, the distance between the tan line and line of support is H by 3, and this H by 3 we have calculated, and this is nothing but our line of support. And the distance between this line of support is called as distance L. That is what we are going to use in our calculation. So L is nothing but the distance between the line of support. In this case, the line of support is an imaginary line which is located at a distance of H by 3 from the tan line. So we have to calculate tan to tan length, plus we have to add H by 3 and H by 3 on both the sides to get the value of length. So let's say this is our length. So how will you calculate this? Length between the line of support is equal to tan length plus 2 times of h by 3 distance. So it becomes 8267.667 mm for this case. So 8100 plus 2 times of h by 3. H we have calculated as 251.5. So this is the length for which we need to analyze this vessel cylindrical shell. So this cylindrical shell will not be utilized or analyzed for 8000, which is only the shell course length, or 8100 mm, which is only the 10 to 10 length, but it needs to be analyzed for the length of 8267.667, because that is the distance between the two line of support. So I hope you are understanding. This is very, very important to find out the correct length which is to be considered in L by DO ratio. So we are done with the length. We have find out the length out of this. Now let's calculate the thickness. Now what is the thickness? OD also we have calculated. That is ID plus 2 times nominal thickness. So we have done with length. We have done with DO. Now what is the T? T is nothing but the first iterative thickness what we are going to assume to calculate the allowable pressure. So as we have seen that for internal pressure, we have already performed the calculation. So in no case we should have this thickness lesser than the one which we have calculated for internal pressure. So what we have calculated nominal thickness as 8 millimeter. So we cannot have the thickness lesser than 8 millimeter to be analyzed. So minimum 8 mm we have to provide. So for that reason, we are starting with this initial thickness of 8 millimeter, whether it is sufficient or not. And remember, all dimensions are in corroded condition. So total available thickness is 8 minus corrosion allowance, that is 1.5. So the available thickness from this 8 will be 6.5, that I should consider in my design calculation. So the thickness will be equal to nominal thickness minus corrosion allowance, that is 6.5. So we have calculated length as 8267.6667, DO as 1016, then T as 6.5. And with the help of these, we will calculate the ratios. So we are dealing with the graphical method first. We will be going to analyze this with the help of both these methods. So let's say L by DO and DO by T ratios, that is what we are going to calculate. So L by DO gives us the value of 8.1374, 8267.667 divided by 1016 will give us the L by DO ratio as 8.1374. And DO by T, as DO is 1016, T we have calculated 6.5, so it is 156.307. 156.307 mm. This is the 156.307. It is a dimensionless quantity since it's a ratio, so don't put any units after that. So these both are the ratios. Now since we have calculated L by DO, DO by T, now we are going to move to the step number 2. We also need to check that whether this DO by T ratio is more than 10 or not. If it is not more than 10, then the procedure is different. As it is more than 10, then we can proceed with the following procedure. So now we are entering in the step 2. In step 2, we are going to calculate the factor A with the help of this L by DO and DO by T ratios. Calculate the factor A with L by DO and DO by T ratios with the help of the figure G given in ASME section 2 part D. These figures are not given in division 1. These are given in section 2 part D, not section 8. It's in section 2 part D. So now we have to calculate for 8.1374 and the value of 156.307. So these are the two values for which we need to calculate the factor A for. So our values are 8.1374 and 156.307. So DO by T is 156 and L by DO is nothing but 8.1374. So let's go in the code and check that what is the value of factor A we are getting. So we are going to open the code. Yes, we are into the code. Which code we are referring to? Section 2. So please remember, we are going to see the section 2 for this. So we are now in the code of ASME section 2 part D in metric version, and in that we have to calculate the factor G. It is given under figures. We have to go to G, that is geometrical chart for the components under external pressure. So this is a geometrical chart. We can see that here there is a factor A on the x-axis. On y-axis, we can see the value of L by DO, and there are various curves for the various ratios of DO by T. If the direct value is not available, we have to imagine a next line which is corresponding to R value, and then we need to see the intersection between this DO by T and L by DO, and then we have to project it down to get the value of factor A. It's so simple. So we have to take the correct value of DO by T, then L by DO. We have to find out or locate the intersection, and then we have to project it downwards on the x-axis to get the corresponding value of factor A. So let's say in our case, what are our values? Our DO by T value is 156.3. So let's say you can see it from here, DO by T, the minimum value given is 4. So if it is below 4, we cannot have the intersection. So above 4, we can say that our value is 156. So it is 40, 100, 150 and 200. So in between these two. So we can say over here, from this distance to this distance, the value is something around 150 and 200. So the difference will be 50. So this to this will have the 50 as a difference between them. So if I split this in 10, then each of the value will be of 5. So this will be 5, 10, 5, 10, 15, 25, 30, 35, 40, 45 and 50. So this is 50, this is 150. So here will be 175 exactly at the middle. So we can say if I logically divide it, so every single line, if I divide it in 10 number of equal parts, so every single line will be of the difference of 5. Our value is 156. So we can say this is the center. So this is the line, imaginary line that is at a distance, which is the 1/10 of the distance. We can say it is giving me the value of 155 or 156. It is very close. As it is a graphical method, it is not the absolutely correct method. So it gives us an approximate value. So don't be very cautious about this thing that nobody will get exactly the same answer. There will be some variation, but that variation will be always within limit. We also going to calculate the factor A value with the help of tabular method, and we are going to compare it. So we'll better understand how much error we can get in this. So let's say we are starting with this 156 is somewhere here. What we need to do, we have to follow this path in parallel, and as it is getting bent from here, so we are also going to bend it from here, and then we need to check our L by DO. Our L by DO is 8.1. So here 8 to 9, this is 8. Again, if I divide it in 10, then the first line will represent 8.1. So something here 8.1 is there. So let's have a look into this. So 156 will be something here. So I am passing parallel to this line as like this, and also having an intersection of 8.1. So I am here. So this is the line for 8. This is the parallel line what I was traveling to with the continuous distance. So 8.1 will be somewhere up, and this line will intersect somewhere here. So we can say this is the point which I need to locate at the downside on the x-axis. So what is this value I am getting? This is 0.4 times 0.7. This is 0.4 times 0.1, 0.4 times 0.2, 3, 4, 5, 6, 7, 8, 9. And then when it becomes 10, it becomes 0.3 times 0.1. So now our value is here. So what is this value? 0.4 times 0.7 and plus this is 8. So it is in between 7 and 8 exactly at the center. So we can say that our value is 0.4 times 0.75. Our value is 4 times 0.75. So let's look into what value we have gotten. 4 times 0.75 is the value of factor A, what we have found out from the ASME section 2 part D, figure G for respective L by DO and DO by T values. So we have projected that L by DO from the left side and DO by T from the top side. The intersection we have plotted, or we have translated on the horizontal axis, and we have gotten the value of factor A. In this case, it is 0.000075. So we have calculated the value of factor A in this case. Now, what is the next step? Identification of the correct material temperature chart for the given MOC. What is our material of construction? SA516 grade 70. So for that, what is the correct material temperature chart? So again, we have to go to SME section 2 part D. Allowable stresses value from where we'll get? We'll get from table 1A. So I am going into the tables and table 1A to identify the allowable stress for the 51670. Right? So this is, now we'll search for SA516 grade 70. So let's say SA516 grade 70 is the value what we are looking for. Line number is what? 33. We are into table 1A. Why we have come to this, or why we are here? To find out what is the applicable external pressure chart. So this is 33. What we have found out, we move to the next page. In applicability column, just next column to that is external pressure chart number. So for line number 33, the external pressure chart number is CS2. So CS2 is the value, or the CS2 is the correct chart what we have to found out, or CS2 is the correct chart what we need to refer to calculate the respective value of factor B. So first what we have done, we have identified the value of, or the correct external pressure chart number for line number 33 or our MOC, that is 51670. So we have found out that for SA516 grade 70, the correct external pressure chart is CS2. And now in step 4, we are going to calculate the value of factor B under this chart CS2. So again, we are now found out the value of the correct material temperature chart CS2, and now we are going to calculate the value of factor B. So again, we are going to get into the code. Now, as we are referring to the graphical method, we have to go to figures and not the table. If we are looking for the tabular method, then we have to go into the tables. Now, since we are dealing with the graphical method, we have to expand the figures, and in that you can see there are various charts. So in that, CS2 is the chart what we are looking for. So now we are into the correct material temperature chart for SA516 grade 70. Now we need to check that where is our factor A and how to calculate that value of factor B from that. So there are two possibilities. One, that factor A will fall under this curve or right side of the curve. If it falls under the curve, with reference to the correct temperature line, we will calculate the intersection with factor A, and that we project horizontally to get the value of factor B. If it falls on the right hand side, then we will extend the respective temperature line and see the intersection, and that will give us the factor B. But if falls on the left hand side, we are not having any method to get the factor B from this. So let us see that our calculated value 4 times 0.75 falls on the left or on the right side of. So let's say 4 times 0, 1, 4 times 0, 7, and our value is 4 times 0, 7, 5. So it is in between these two. And as we can see that it is not under or right side of the curve, but it is on the left side of the curve. So we will not get the value of factor B for this case. So as we can see that for this particular case, the factor A falls on the left hand side of that curve, and hence factor B cannot be calculated. Now what needs to be done? In next step, since we are not able to calculate the factor B, so we have to calculate some other factors to calculate the allowable pressure. What are those other factors? Now we need to calculate the value of E, that is the Young's modulus of elasticity. From the external pressure temperature chart, we just have seen that. And from that, we have to calculate the value of E now. E is the Young's modulus of elasticity. Again, we have come into the same table or the chart, we can say. Our temperature is 150 degrees Celsius. So up to 150 degrees Celsius, this is the material temperature. line what we have to follow. If our temperature would have been 200, so it is 150, it is 260, so it would have been somewhere in between. So we have to project or parallelly draw the line which is going parallel to this curve to get the respective curve. Since in this case we are having 150, the curve is already available, and from this curve we have to get the value of Young's modulus. We don't have to go to table TM1, that will not the value we are looking for. For external pressure chart, we have to take the value from here only. So let's say for 150 degrees Celsius, we are having for this curve the value of 200 into 10 raised to 3 MPa. 200 into 10 raised to 3 MPa is nothing but 200 GPa. This is the value of Young's modulus. That what we need to use in the formula. If it is in between these two, then 150, 200, 260, and these two values are there, then we can simply interpolate and get the corrective or the correct value of Young's modulus. In this case, we can directly have that as 200 into 10 raised to 3 MPa. So from this material temperature chart, we have found out that our temperature, our Young's modulus value is 200 into 10 raised to 3 MPa. So now we are having the value of Young's modulus. We also have factor A with us. Now we can calculate the allowable pressure in step number 6 by the formula allowable pressure is equal to 2/3 of AE upon DO by T. So 2/3 in bracket AE upon DO by T. Now we have the value, whereas A is the factor A, E is the Young's modulus, what we have calculated, and DO by T is the ratio. That is what we are already had, 156.307. So with the help of these values, we can calculate the allowable pressure. If we would have calculated the factor B, then this formula would have been different. That would have been 4 by 3 B upon DO by T. But now, since factor B is not available, this is the formula we have to use. So let's put the values in and we will get the answer. We have calculated factor A as 4 times 0.75. Young's modulus value 200 into 10 raised to 3 MPa, and DO by T is 156.307. So we will get the allowable pressure as 0.063975 MPa. Now what is our design value? 15 psi. So let's convert 15 psi in MPa. So how to convert? With the help of the conversion factor. What is the conversion factor for this? It is 145.0368. This is the value by which we need to divide the 15 psi or the psi value to get the value in MPa. So 15 divided by 145.0368 will give us the value of 0.1034 MPa. So our requirement is 0.1034, and what we have found out is 0.06. So our 0.06 is less than 0.1034. And the selected thickness is not sufficient to sustain for this full vacuum condition. Then we can say as PA by P, PA is less than P, selected thickness is not sufficient. We have to choose one of the following options. So what are the options available next to us? As it is a iterative method, in the first case, in the first iteration or in the first calculation, we have found out that it is not sufficient. The thickness, whatever is there for internal pressure, that thickness is not sufficient. Now what needs to be done? There are three options available. Option number 1, increase the shell thickness and repeat the procedure what we have done. And again we have to calculate the allowable pressure and we need to compare that with design. If it is more than design, the design is safe. Again, if it is not, then again we have to go back, increase the thickness and repeat the procedure. That's why it's an iterative procedure. So increasing shell thickness is one option. Then we can employ a stiffener. We can add one stiffener or we can add number of stiffeners to reduce the length and hence the L by DO ratio, and because of that the factor A will be more, factor A is increased, so factor B will increase, and hence the allowable pressure will also increase. So cutting down the length, that is one more thing with the help of stiffeners. So we can have this option 2, that we can add on the stiffeners and again check the allowable pressure, and if it is more than the design, then our design is true. And the third option, it could be a combination of both, that we will be adding few stiffeners and we are also going to increase the thickness of the shell. So what is the first option that we always look for? So increasing the shell thickness for this entire length is not a very economical thing. So it is going to increase the weight and the cost significantly. So this is not the first option what we always going to choose. So let's start with the option number 2, which is the most economical, where we'll be having one ring just be given to that shell And if it is going to increase the allowable pressure more than design pressure, then there is no other requirement that needs to be satisfied. So option 2 is the most economical. So let's say we are going to start with this, the addition of the stiffener ring at the center of our shell.
Static equipment design was never so easy without express engineering solutions. Understanding code and manual calculations, made simple and interesting with our professional and expert training courses. Attend the training courses as per your convenient time, speed and location, without compromising your work schedule. Become an expert with easy to understand, detailed and comprehensive video lectures. Select from a wide range of courses like pressure vessel design, heat exchanger design, PV Elite software training and FEA using Nozzle Pro software. Understand the latest changes in the ASME Code 2021 and PV Elite PV24. Get answers to your doubts in weekly live Q&A sessions. So, don't delay anymore and download our app. Call or write to us for more details and offers. Expand your knowledge and skills with our highly established training courses. Because no one can decode the code like us. Brought to you by Express Engineering Solutions, your true partner in training.